In this video, we're going to look at binomial probability distribution. So the prefix bi intimates two things. So a binomial probability distribution is a chance experiment that has two outcomes, and we're going to call the outcomes a success with a probability of P, or not a success with a probability of Q. And the way that this works for binomial distributions is the trials that we're going to do are going to be independent. So what we're talking about is we're talking about chance experiments where there's two outcomes like we've got here. Each of the outcomes is independent of the other, so whatever happens on this first one doesn't impact on this second trial, doesn't impact on the third trial, and the probability of success needs to be the same, needs to be consistent all the way through. So here we've got a chance experiment with two outcomes, and we've got three trials. We get all of our outcomes together, we classify them with a discrete random variable, and we pull together their probabilities by multiplying along the tree. So along this first one, the probability of success, so the probability of success we're defining as being heads. So this branch is P times P times P, or P cubed. And then we go along the branches and work out the probabilities all together. So binomial distributions have to do with chance experiments with two outcomes. The other part of the word, well, the whole word binomial, has to do with our work with algebra, and a binomial expression is an expression that has two terms in it. So let's go with just simple A and B for our two terms. And what we're going to look at is we're actually going to look at specifically binomial expansion, where you take those two terms as a unit and you raise it to a particular power. So we've done this thing before where we've looked at perfect squares and we've looked at perfect cubes, and we get patterns in our binomial expansion, and we're going to tie our binomial expansion together with our probability experiment to define what a binomial probability distribution is. So to come up with this definition, I'm going to take us through some trials, some different number of trials, and actually look at the tree diagram and generate some probabilities for our discrete random variable here. So this time we're going to do two trials of flipping a coin. So heads and tails, heads and tails. We're going to define our probability, a success, as being a heads, and so our probability of success is P. So on this branch, if you like, we've got P as our probability and P as our probability. For a tail, the probability is Q. And so to work out the probability of two heads, where X is the number of heads, we have P times P, which is P squared. One head and one tail is P times Q. One tail, one head is Q times P, or P times Q. It's exactly the same thing around, the other way around. But again, our number of heads here is just one, and then the probability of two tails will be Q times Q, which gives us Q squared. When we put our probabilities together in a table, in a probability distribution table for 0, 1, 2, and 3, what we get is that the probability of getting no tails, which is this one here, is Q squared, so that goes in here. The probability of getting 1, we actually have multiple occasions where 1 occurs. So we've got 1 here and 1 here, and so to find the probability of X equal to 1, we actually add these two together. So PQ plus PQ gives us 2PQ, and of course finally 2 heads is just P squared. So what I want to draw your attention to is this pattern in the probability distribution table in comparison to our perfect square expansion. Can you see a pattern? Can you see a relationship? Let me move that up there. Okay, let's look at 3 trials. So this is the tree diagram for 3 trials. 1, 2, 3 trials. These are all of our outcomes, and we've let x be the number of heads. So we've got 3 heads on this branch, and so our probability will be p times p times p, or p cubed. We have 2 heads on this branch, so it'll be p squared, and one of those other outcomes will be a tail. So if we go through and again summarize that information into a probability table for 0, 1, 2 and 3, what we've got is for p, x is 0, which is this branch here, is p cubed. For x is equal to 1, we've got a few of those, and so we actually have 1, 2, 3 of them. Sorry about that, a little bit messy, but that is where our 3 lots of p times q squared come from. For our 2, we also have 1, 2, 3 lots of them, and this time it's 3 times p squared q. And then finally x is equal to 3 gives us p cubed. And again, let's compare that with the binomial expansion of a cubic. See a relationship here? Starting to get the idea? Let's look at 4 trials. So here's the 4 trials I prepared earlier. So we've got 4 results in each. So x is equal to 4. 4 heads will give us p to the power of 4. 3 heads and 1 tail is p cubed q. This is also p cubed because there's 3 heads and a single tail. And when you summarize it all together, so we have x is equal to 0 is just this last row, so q to the power of 4. We have 4 lots of x being 1, so 1, 2, 3, 4 of them. X equal to 2, we've got 1, 2, 3, 4, 5, 6 of them. So we'll have 6 lots of P2, Q2. And then x is equal to 3 is 1, 2, and 3. So we've, hang on, we should have 4 there. 1, 2, 3, 4. There they are. So we've got 4 of those, each of which has 3 heads, so P cubed, and 1 tail. And then finally, the 4 is just 4 heads multiplied, their probability multiplied together. And again, have a look at the binomial expansion of a plus b to the power of 4. Let's look a little bit more at this pattern. So here's a summary of some of our binomial expansions. So a plus b all squared, a plus b all cubed, a plus b to the 4, and a plus b to the 5. And there's a whole heap of patterns in here, and I want you to pause the video and see if you can find these particular patterns. And so what I'm looking for is a pattern for the powers of a as we go across for one of the expansions. What's the pattern that happens with the powers of a? What's the patterns that happen with the power of b as we go across? What's the pattern for the powers within a particular term? So the powers within this term, the powers within this term, the powers within this term. What's the pattern? What's the relationship? Can you see it? Have a look at those, and then I'll talk about the pattern in the coefficients in just a minute. So our first pattern is that the powers of a decrease from whatever that power is for the brackets down to 0. So let's have a look here. So we start at 2, so we've got a to the power of 2. A by itself is a to the power of 1, and it doesn't look like we've got an a here, but it's actually a to the power of 0, because anything times raised to the power of 0 is equal to 1. And so let's have a look at the next one. This is to the power of 3, so our powers go 3, 2, 1, a to the power of 0. Our powers of b do the opposite, they increase from 0 to n as we go across. So let's have a look at those. So let's look at the top one here. So we've got b to the power of 2, and so we're going to start with this first term here. We're going to squeeze in a tiny little b to the power of 0 there, and then we've got b to the power of 1, and then b to the power of 2. On our next one, where we've got to the power of 3, let's start at the other end. B to the power of 3, b to the power of 2, b by itself is to the power of 1, and so this one in here I'm going to squeeze a little b to the power of 0. And the powers within a term, if we look at these, let's look at these terms up here. The powers in those terms, the power in that term, the powers in that term, they all add to 2, which is the power that we were working with for our binomial expansion. Let's have a look at this one. They add to 3, they add to 3, powers in that add to 3, powers in that add to 3. The powers in the coefficient are a little bit more difficult to generate, but I'm going to show you how we'll do that now. So here's a summary of the different binomial expansions, and I've included a plus b to the 0 here, so anything raised to the 0 is 1. I've also included coefficients for every single term. So here we would normally have just a squared plus 2ab plus b squared, but including coefficients here. Let's have a look and see what happens with this little video when we get rid of the a's and the b's. Watch what happens. We create this little triangle shape, and there's definitely patterns there. Let's have a look again. So what we do is to get rid of the a's and b's from the terms. We just take the coefficients and we rearrange them, and we get this triangle. Now this triangle is what we call Pascal's triangle. And we can use the patterns within this triangle to generate our coefficients for our terms in our binomial expansion, and hence we can use it to find the probabilities for our binomial probability distribution. Let's have a look. Okay, so one of the patterns is that every row starts and finishes with a 1. A 1 and a 1 and a 1 and a 1 and a 1 on each end. The second element in every row increases as the rows go down. So 1, 2, 3, 4, 5. Now, to generate from one row to the next row, what you do is you take the two numbers up above and just off to the left and the right, and you add them together. So 1 plus 2 is 3. We take the two numbers to the left and the right and add them. 2 plus 1 is 3. You can do that in the next row as well. 1 and 3 make 4. 3 and 3 make 6. 3 and 1 make 4. So using that pattern, you can generate as many rows as you like. So go ahead and generate the next row using that pattern. Press pause, have a go, and then I'll put the answer up. How did you go? Did you get your 1 on each end? And then 6, 15, 20, 15, 6. You'll notice that it's actually symmetric too, that 15 and 15 are the same, 6 and 6 are the same, and that's the same on this row. 2 10s, 2 5s, a 6 in the middle, 2 4s. So it's symmetric down that centre. If I go down the centre there, it's symmetric down the centre. The other way that you can look at these numbers and generating these numbers is through the use of combinations. And so you can use combinations to generate the numbers 1, 1, 1 as the next row, 1, 2, 1 as the third row, 1, 3, 3, 1 as the fourth row. And so you can see that there is a pattern in how you use combinations to generate those coefficients as well. If you've never used combinations before, this is how I like to think of combinations. From n things, how many ways can you choose r things? So it's written as n, the number of items that you've got to choose from. C, it's not technically not choose, but from n, choose r. So for example, 0, C0, you can think as from 0 things, how many ways can you choose 0 of them? And there is one way to do that, and that's by choosing nothing. From 1 thing, how many ways can you choose 0? Again, one way, and that's by doing nothing. From 1 thing, how many ways can you choose 1? And that's one way, by choosing the item that's there. It's a little bit silly for these lower ones, but the next few will make sense. From 2 items, how many ways can you choose 0 of those items? And that's 1 by choosing nothing. From 2 items, how many ways can you choose 1? Well, there's 2. You either choose the first thing or you choose the second thing. So that's 2 different ways. And then from 2, how many ways can you choose 2 items? Well, that's one way. You have to choose both. And so as you can see, as the number of items gets larger, you get more ways of choosing. So you can choose none, 1, 2, or all 3 items at once for 3 items. For 4 items, you can choose no items. You can choose 1 item, and there's 4 ways to do that. From 4 items, there are 6 ways to choose 2 items, etc., etc., etc. I'll show you how to do this on your CAS calculator and by hand in another video. But for now, just follow the pattern. So I'll give you a minute, because we're looking at patterns, I'll give you a minute or 2 to just pause the video and look at the patterns. What do you get when you've got some number at the top and it finishes in a 0? Some number at the top and it's got a matching number at the bottom. And what do you get if there's a 1? Or if whatever the number is at the top, the number at the bottom is 1 less than that. Fill in the patterns for me. So hopefully you got that the first 2 are 1 and that the second 2 are whatever the n value is at the top. And so from that pattern, you should be able to work out very quickly these examples. Pause the video, write your answers, and then I'll put my answers up. So finally, let's look at how you go about predicting the probability of an outcome for a binomial probability experiment using all of the stuff that we've gone so far. So the first thing you need to do is to recognize that the number of trials for an experiment is going to be the number at the top of your combinations. So this has 0 trials, choosing 0 items as 1. Doesn't seem to make much sense. But the next one says from 1 trial, what's the probability of not getting an outcome, which is 1, and from 1 trial, what's the probability of getting 1 outcome? Let's look at the 2 trials and it will make a bit more sense. So here's our 2 trials. and you can see the patterns from before. 2C0, 2C1, 2C2. Let's have a look at that in conjunction with our probability distribution table over here. Let me just move this out of the way and see how that relates. I'm just going to zoom in over here for a minute. So this is our probability table for the number of heads that we got from 2 trials. So 2 trials, the number of heads that we got. So we can generate our probabilities if we look at, so this was the outcome for no heads. So the 1 is generated by this 2C0. Our P is raised to the power of 0 and our Q is raised to the power of 2. That gives us that. 2C1 will give us the 2. And we look at our increasing powers of P. So this is P to the 0, P to the 1, P squared, that's a squared there. And our decreasing powers of Q, Q squared, Q to the power of 1, Q to the power of 0. And what we actually end up with is a relationship between the probabilities and the actual formulas themselves. Can you see a pattern here? Does the pattern repeat here and here? And if so, what is that pattern? If we look at a cubic distribution, which is from our 3 trials, so 3 trials for this one here. Let me just zoom back out a little bit. So now we've got 3 trials. There's our Pascal's triangle. Just there, there's our Pascal's triangles and our numbers generating our coefficients here. So let's have a look back at this table and look at the relationship between the values in that table and the combinations that we use to generate the numbers. We're missing a number here. That should have a 1 there, and it should have a 1 on the end. And again, you can see that there are patterns here. Seeing the patterns? Let's have a look. Can you see a relationship between what's written here, the number of trials that we did, and the outcomes that we get? So let's have a look and see if your pattern is the same pattern as what I got. So to calculate the probability of X successful outcomes in N trials of an experiment, where the probability of success is P and each trial is independent of any other trial, this is the pattern that we use. So the probability that X is equal to some particular number of successful outcomes is the number of trials in combinations with the number of successful outcomes. Your probability of success has to be equal to X. So if you want 3 outcomes, you need 3 successes. And then your probability of a failure or not a success, a Q, is N minus X, because these 2 powers have to add to N. So this is an important formula, and this is a formula that you need to know. It does appear on the formula sheet, and it looks like this. And I'll show you how to calculate NCR or NCX here. You'll see that they've got it written in a different format on the formula sheet. So they've just replaced the C with these 2 curved brackets. It means exactly the same thing. And I'll show you how to calculate it by hand as well as using your CAS in the next video. But before we do that, we need to learn how to decide whether we can actually use this binomial probability at all. And so we'll look at our conditions that are required. So for the situations where we've used binomial probability, what we've had is two outcomes. So we've had the tree diagram where each time we split it, we had two outcomes. And we label these outcomes as being either success or not a success, or a failure, if you like. The probability of success is constant, so it doesn't change at all. And each of the trials in the experiment is independent of each other, so that the probability of success is the same no matter whereabouts it is on the tree diagram. And the probability of failure is also the same no matter where it is on the tree diagram. If we have these three conditions, then what we've got is a series of trials, or a sequence of trials that we refer to as Bernoulli trials. And this is what we're looking for to see if we can use binomial probability. So if we have a situation where there's two outcomes, the probability of success is constant and each of the trials is independent, then we can go ahead and use our binomial probability.